Okay, so today we'll learn about the domain and domain world, which one is very important in spectronics applications because we will store the magnetic information or digital information as a direction of the magnetization. So different domain means different informations, and also domain world is kind of separation between two domains. So sometimes if we can manipulate the portion of domain world, means we can change the size of the domain. So it's closely related with the information storage. Okay, so I already mentioned how why the domain is formation. Because to reduce the total energy of the magnetostatic energy, when we make the smaller domain, the magnetostatic energy is getting smaller. So here is one question. How small domain is has a energy minimum? As I said, if you reduce the domain size, you can reduce the the magnetostatic energy. It sounds smaller domain is better, right? But how small? Yeah, I didn't mention about one more energy, what we call the domain wall energy. Domain wall energy is kind of surface energy. They are formed in a domain wall between the boundary between two domains. There is some special spin structure. That's what we call the domain wall. And this domain wall energy is always positive. So it means if we have a more domains, we have a more domain wall area. Then the total energy is increased. So please remember that domain wall energy is kind of domain wall, the energy density unit of the joule meter square. So when we multiply the area of the domain wall, we got the total energy. So for the given domain wall energy, the system want to reduce the domain wall surface area. You can imagine the kind of a bubble. When you make some soap bubble, they make some sphere shape. Why they form the sphere shape? Because they want to reduce the total energy, because the surface energy of this kind of a bubble is usually positive. So they try to reduce the total surface area. And that kind of thing is you can easily found in many physics, like in a water, in a small drop, you have such kind of bending of the water because of surface energy difference between the glass surface and the water surface. So anyway, everything is about the energy. If you define the energy, the system prepared the smaller energy. The important thing is you do not miss the important energy term. If you miss some important energy term, you got an incorrect result, right? So if you consider the correct energy term, the remaining problem is just mathematical treatment to find the minimum energy. Okay. So this kind of hysteresis loop is kind of process of the energy minimization, the given field. Okay. Yeah. Mm-hmm. And analysis energy. Yeah. That's the first order approximation. If you think about more precisely, we should include the dipole energy. But usually the contribution is not significant compared to these main terms. So sometimes we ignore this dipole energy term, but sometimes we need to take care about this kind of dipole energy also. I'm going to explain it. Okay. So the formation of domain is kind of energy minimization. And in generally, ferromagnet consists of multi-domains. And with the external magnetic field, we form the single domain. We apply the strong magnetic field. Otherwise, they form the multiple domains. And for example, this kind of shape of domain is what we call, there's some special name of this kind of domain or structure. This is called Landau patterns. So as you see here, the marginalization of each domain has this form, and there's no stray field in outside of ferromagnet. So it's one of the lowest energy state. But it's very simplified version. The reality is a little bit more complicated, but please remember that somehow the system want energy minimum. So always we need to find the energy minimum condition to figure out which domain configuration is stable one. Okay. So then what is the domain work? This cartoon tells us if we have a one spin in one domain, here let's say blue, and the red one is south, which one is pointing down. And between these two domains, the one direction is up, the other direction is down. And what is the spin direction between them? Yeah. If you take a look at this cartoon, maybe you can say, okay, it sounds makes sense because there is some slowly rotate. And from here to here, they make some continuous variation, and finally, they found the up and down domain at the end point. And here is the question. What is the this domain world width? What kind of physical energy will determine this domain world width? Okay. Then there is two important energy is involved. Okay. The one is why this domain and this domain pointing only up or down instead of the other directions. What is a possible source? Preferred direction. This is what we call the analytic energy. So if you have a uniaxial analytic energy, uniaxial means upspin, downspin have the same energy. But if they pointing the other direction, we have a increased amount of energy. Depends on the angle theta. Which one is form of the cosine theta square for the uniaxial analytic energy. So that means all these spin guys has a increased amount of energy. And we are working on a ferromagnetic material. So in a ferromagnetic material, all spins try to parallel state. So when they rotate the spin a little bit between the other neighboring spins, there is cost of the exchange energy. So these two energy, okay, the analytic energy make the spin parallel to up or down state. They do not like the rotating state. Okay, and exchange energy won't make them parallel. So, in the sense of the domain world width, let's assume domain world width is infinite. Then the tilting angle between each spin is infinitely small. So the cost of the exchange energy is getting smaller. So that means exchange energy try to push domain world width is wider. And how about the analytic energy? If we have such kind of rotating spins, they cost they pay some energy cost for the analytic energy, and number of spin of this direction is smaller, then the energy cost is reduced. So they try to make a shorter domain world. Okay, so one energy try to expand, the other one is reduced. Then what's the solution? They should be trade-off. So we need some minimum between them. That will determine the domain world width. Okay. So anyway, the domain wall forms, to minimize the system energy. And as a result, the domain wall width and this is domain wall width and this is domain wall energy density. Actually, this is energy density. As a form of these two equations. Okay. So Yeah. This is third homework. The second from third homework is finding this relation by yourself. Any kind of mountain related textbook, there is some details of these mathematical descriptions. And actually, this is the kind of energy minimization process. So you need to understand about the variational technique, the variational method to obtain this result. But you may just copy of the textbook to solve this problem number two, but you need to understand the procedure. Okay. So anyway, this is the result. And as I said, the A is exchange energy. Is exchange energy. So large exchange energy means domain wall width is increased. That's what we already understand. If you the ferrite layer prefer the polarization, that means domain wall width is increased. And the anisotropic energy is getting larger, then domain wall width will shrink down. So actually the number of the spins involved in the domain wall, the total energy is roughly say something like this. So the minimum of number of atoms, number of spins involved in the domain wall is obtained by minimize of this one. So this is very simple mathematical example. I believe you guys learn in our high school. They form something like this. So this is the very simple derivation of this domain wall energy. And once you obtain this result, you can say this equal is hold when A is B is same. So if we put it, you got this number, the domain wall width. You may cannot get these specific numbers, but you can easily obtain this behavior. Okay. So anyway, I hope all students solve the homework by yourself with the help of the textbook, and you can easily obtain this result. And this result is very important in many spintronics applications. So please remember this result. Okay, so this is about the 180 domain walls. For the 90 domain wall, we have also domain wall energy expressions, but it's not usually very important. But you may take a look some textbook. Okay, and there are in this case domain wall here. The spin is rotating. For example, if this is up spin, this is down spin, then they're rotating something like this. But this is not the only way. There is the other way. If you have a spin here up and down here, some kind of domain wall forms such direction. And this one is looks like rotating the for example, this is the x-axis, this is y and z. So this one, all spins belong to the xy plane. And this one is the spin is belong to the yz plane. So that's the difference. And these two kind of domain wall is what we call the block domain wall or the Neal domain wall. Yeah, this is the one domain and the other domain. And block wall, the spin is rotating. And for example, this is x-axis, this is y-axis, and z-axis. And in this case, spin is rotating this is G, YG plane. And in this case, the spin is rotating XG plane. Okay. And these two spin states has a same energy term of this equation. But as you Doyon asked, these two domain world has a little bit different energy because of the different magnetostatic energy, the dipole energy. So we need some extra term to describe correctly for the logon and the needle. But in many cases, this term is not important. So usually we say the domain energy is this equation. But if you consider the film thickness, this is general. In a thin films, the needle has the smaller energy. Here, this is the wall width, not the energy, but in a sense of the energy, needle has the smaller energy for the thin films. And for the thick one, they have a usually blue wall energy. You can easily imagine, in a blue wall, in this case, we have a surface pole at the top and bottom of the films. So in this case, this kind of extra free fall generates straight field. So when they dig, the forming this kind of free fall, they do not pay the cost of energy. But in a needle, the free fall is formed inside of the films. So when film is getting thicker, blue wall costs more energy, so they free for the needle. So look at this. The film thickness across the needle and blue wall is around tenths of the nanometers. So when we playing with the thin films, ferromatic thin films for the spintronics, usually we are working on less than 10 nanometer. So always they prefer the nil type domain one. But the reality is more complicated. I'm gonna show later. But now what you need to is understand the 180-degree domain walls and how you can obtain this domain wall width and the domain wall density. As I said, this is the joule per meter square unit. And also, you can obtain this result by considering the dimensional analysis. As you already said, all important energy term involved in this domain wall is exchange energy and the RSP energy. And the exchange energy unit is the joule per meter. And the RSP energy density has a unit of the joule divided by meter cube. So to obtain the length, what you can do is divide these two terms and taking the root. Then you got the length scale. Okay. And how about the energy? We need multiply these two guys, and if we multiply these two, we have this result. So we got the joule per meter square, the surface energy term. This is another the most simple estimation of this energy form. Okay. And as we already mentioned, in a ground state, the usual ferromatic material has this kind of random domains. And when we apply external field, they form a single domain. That's what we call saturation. And depends on the external magnetic field, this magnetization has this kind of curve. This is what we call the MH curve. And this is nothing else but total energy minimization process. But here is one question. This total energy is a function of external field. Physically that is not quite correct expression, because when you're talking about the function, if we have a certain variable, let's say x, and function fx means if we have a x, we need to define this function value. This is called but in this hysteresis loop, for the given field, we have two different possible values. Why it is possible? Because we are finding energy minimization, but this energy is not the local energy minimization, not the global energy minimization. It sounds maybe difficult, but I'm gonna explain later. But anyway, it's kind of energy minimization, but we are looking for only the local energy minimum, not the global energy minimum. Okay. And this kind of image curve is very important because this image curve shows the basic characteristic of the magnetic materials. So there are many kind of techniques to measure this kind of shape of loops. And the most famous one, most popular one is VSM. This is the vibrating magnetometer. You can directly measure the magnetic moment of the samples using the VSM. And they measured actually magnetic moment directly. And the MOOC is kind of optical technique, and they using the magnetic optical co-effect, which one is when we irradiate a polarized light in a ferromagnetic material, the reflected light polarization is a little bit changed. It depends on the magnetic direction. This is what we call magnetic optical co-effect. So the reflected light has a change of the polarization, and this change of polarization is proportional to the magnetization direction. So we can indirectly measure the magnetization direction by using the MOOC. Also, there are another technique called anonymous Holy path and AMR. We will learn it in a next chapter. And this kind of hysteresis loop measurement, what we call this is technical magnetization. Yeah, why using this name, technical? Because when we learn about the basic magnetism, we talking about the magnetic moment as a function of field, and depends on the temperature, they show such kind of behavior. So this kind of behavior is different of the this technical magnetization. Technical magnetization means only they control the direction of the spins in a domains. In this curve set, they increase the saturation magnetization itself by applying the strong magnetic field. So that's the different point. But in engineering point, we need always the technical magnetization. So we assume the total, the saturation magnetization of your given sample is constant. And by applying the magnetic field, we change only the direction of the magnetization or changing the size of the grain. Okay. And yeah, this is one example. If we have such a Landau pattern domain, if we increase in the field in this direction, this direction of domain size expand and the other domain size is shrink. Or in other words, we can say this domain one is moving to this direction. They're actually same result. Okay. Okay. So now let's back to the most simple case. We consider only the single domain, means all the sample magnetization is always pointing the same direction. So this is the only single domain. Or the other word, the macro spin, means all spins behave as a macroscopic stop. Or what you call the coherent rotation, means the spin direction is rotating coherently in full samples. And when we apply the magnetic field, magnetization is direction changes, and this magnetization direction changes governed by the energy minimization, and this is what we call the Stoner-Wohlfarth model. That is the very basic understanding of the spin dynamics in a most simple case. And these two cartoons is kind of a result of this Stoner-Wohlfarth model. And if you can understand these two figures, then it implies you understand this Stone-Wohlfarth model. Okay, so as I mentioned several times, Stone-Wohlfarth model is nothing else but the energy minimization. We assumed the all your sample is the single spin, single classical dipole. And there are different names: single spin, macro spin, monodomain, coherent rotation. They are all physically same meaning. In this assumption, we're gonna miss many important features. Yeah, it's too simple. This model is too simple. But still, with this simple model, we got a, and this is very useful to understand many real problems. Okay. Yeah. This Stone-Wohlfarth model, we can obtain the switching field means the what kind of field, how large field we need to switch the magnetization. That is very important in application. And also the asteroid curve, which one is this curve, and maybe you can understand what's the meaning of this curve. I'm gonna explain the physical meaning of this asteroid curve. And also with this idea, we can obtain very many predictions, even though this prediction is physically not quite correct, but still they give a many idea of what's going on in your samples. Okay. From now on, I'll be using many mathematical equations, but you don't need to be panic. You don't have any exam, you don't have any text exam, so you can following this kind of mathematical system by yourself very slowly, step by step. Okay, so let's start the single domain, and we assume the uniaxial anisotropy. Okay, if your system is biaxial or differentiable with anisotropy energy, we need different energy. But the key idea is here. The total energy is these two terms. This is the anisotropy energy. This is the Zeeman energy. Okay. So here, to describe the initial anisotropy energy, I'm using the Ku sine square of theta instead of the minus Ku cosine square of theta. These two equations, as we already mentioned, mathematically different, but physically only the difference is constant. So for the energy description, it's identical. But in some reason, we are starting with the sine square. And as we mentioned, this Ku, ionospheric energy, is actually the energy density. So we need to multiply volume of your system to obtain the total energy. And this term is nothing else but the Zeeman energy, which one is inner product between the magnetic field and the magnetization direction. So if we assume the direction of the magnetization and the field direction as an angle of phi, this inner product generates cosine phi. And here, the EG-axis of this initial RSP is angle theta from the field direction. And the RSP energy has a sine square of the phi minus theta. Okay. So the the initial RSP energy is proportional to cosine theta or sine theta between the EG-axis and the direction of magnetization. So this is the phi minus theta. So I hope all students understand this energy description. Is okay? Yeah, please have your own time to understand this equation. This is the most important equation in this today's lecture. Okay, if we have a biaxial system, what term will be changed? This term must be changed something else, like sine square, cosine square, something for the biaxial one. You may remember that the biaxial enhanced energy has a sine square, cosine square. Okay, but the initial one is most simple, so let's focus on the initial one. And okay, now we have a system energy. What we need is finding energy minimum. So let's take the derivative as a function of the phi, which one is the direction of the magnetization. So if you take the derivative, we got this result. And if we theta is fixed because the theta is related to the direction of the field from the EJ of the magnetization of your samples. So theta is in a given problem, theta is a fixed one. And only variable is phi. So the first goal is finding phi, which one satisfies this energy minimization equations for the given material parameter and for the given theta. And this equation looks not that complicated, but unfortunately, we have assigned something with phi minus theta. So general solution of this equation is not easy. So let's start the easiest way. Let's assume theta is 0. So that means the field is applied to the EJ direction. Or the parallel or anti-parallel to the EJ axis. So means field can be this way or this way. Okay, so let me simply ask, if you apply magnetization here and if you apply field this direction, then the magnetization direction, maybe if you apply strong enough field, they try to align the field direction. Because this direction is make the lowest energy for the Gman energy and the RSF energy. So there is no reason the magnetization is pointing the other direction. And how about if we apply the field the other direction? The magnetic moment, the magnetization direction is here. And if you apply strong enough H field in a negative direction, they pointing this direction. But if you apply the very tiny small field here, what happens? That is what we want to solve now. Okay, so let's focus on set as 0 case. So if you set as 0, this equation is getting much simpler. So we have this simple form. Okay. So we have two solutions. One is sine phi is 0, and the other one is cosine phi. We solve this one, you can this result. Okay. And when we solve this kind of energy minimization, not only the first derivative, but we need the second derivative. We need to check the second derivative sign. So let's take the second derivative. Okay. And the second derivative for the phi is 0. We have a positive when they satisfy this condition. And when phi is pi, we have this result. We can insert phi to here. Phi is 0 or phi is pi, got this result. And this second derivative must be positive to form the stable condition. Okay. So in this equation, what you can say is to stabilize this condition, phi is pointing to the field direction, they should satisfy this condition. Or if they fail to satisfy this condition, in the other word, this one, they are unstable. And when the magnetization is pointing on 800 degree, they are stable only this condition. And when they satisfy this condition, it becomes unstable. Okay, what is the meaning stable to unstable? If the energy is stable, they are staying here. But if they are unstable, they won't go the other way. So that is the switching. So when field is satisfy this condition, this state is no more stable. They're looking for another state, more stable state. So that means when phi is 0 means if we have a field here and we have a saturation of magnetization means this is the phi is 0. They are parallel to the field. They are stable, but when they reduce the field and change the negative sign, and when they satisfy the specific value, we call this is the HK. We're gonna using this one many times. HK defined by 2KU divided by mu0 ms. Okay, we have a minus HK. Then this is no more stable. So they looking for more stable point, and the more stable point is corresponding the reverse direction. So they switch at this point, minus HK. And then if you increase more negative field, then they are still pointing I direction. Okay, so let's back the field to this here. And once they reach the plus HK, this is no more stable. So they start to switching back. So we obtain this kind of nice hysteresis law. Okay? That's why this quantity is very important. Okay, so look at this. Please remember that when you multiply ms, he, b0, this is always energy density, the unit of the energy density. And this is the also energy density. So if you rewrite this equation, this form. So this is the Gman energy, which one is preferred the field direction. Magnetization preferred field direction. And what's the meaning of this Ku? This is the energy preferred the specific and specific energy directions. So this means the double means the two means the up from the energy is Ku sine square theta case. Here we are using phi in this notation. This is the phi, and this is the Ku. Okay, and this is kind of energy barrier. So from here to here is switching. So to overcome this Ku, the energy barrier, you need such kind of energy from here to here. And this energy came from the Gman energy. So this is proportional to here. Okay. So always we have H multiply mu0 ms generate energy density, and this term is another energy density to compare the competition. Okay, so let's back to the more details of the mathematical descriptions. Okay. Okay, so far we talking about the first solution of this equation, and next the second term. Second term generate cosine phi satisfy this one, and look at this. This one is nothing else but HK. Okay, we're gonna using this HK several times. So when cosine phi is minus HK over H, then the second derivative is always negative. So that means there's no stable solution satisfy this condition when angle theta, the field direction is 0 or pi. Okay, so uh, we what we obtained is from this idea, we can say the field and the magnetization has such kind of very well-defined square roots. And the switching field is HK, each one is defined to KU over mu0 ms. Okay. And this is what we call the Cauchy field also. And now we solved only when theta is zero case. Now let's talk about the more general case. So as I said, we defined this term is analytic energy, analytic field, HK. And let's introduce the dimensionless small h, which one is divided by external field by HK. And the total energy divided by 2KUV make a more simple form of the energy equation. This is the actually same energy equation with this one, but we need a more simple form because we are playing with more complicated mathematical case. Okay. So we have to repeat the same procedure for the energy minimization, taking the derivative with respect to phi. And we got this result, and we take the second derivative, and we found this equation. Okay. And for the given field H, which one is defined the external field by HK, we can determine the direction of the magnetization from this equation. But this is a trigonometric function, so there's no clear analytic solution of the angle phi, but we know the angle phi is function of external field and the direction of the magnetization. Yeah, the functional form of this one is not easy, but this magnetization direction angle it depends on the field strength and the direction. Is okay? And let's make the introduce new variable small m, which one is normalized magnetization. And actually, this is nothing else but the cosine phi. Okay. So from this equation, we can change multiply 2 here. This equation is here because we say cosine phi, m is cosine phi, and the sine phi is plus minus root 1 minus m square. And yeah, you can find this equation by changing the m is cosine phi. And by the law of the trigonometric minus, you can obtain this one. And we change the sine phi by root 1 minus m square and so on. This is the now function of m and theta and h. So the goal is finding the m for the given theta and h, and it looks very complicated, but somehow we obtain the equations. Okay. So let's think about the magnetization direction angle is fixed. Actually, we already did about the theta is 0 and phi case, and you can repeat again. When theta is 0 or phi, you can simplify this equation in this form. Okay. Then, how you can make this 0 in this equation? There is two ways. One is m is plus minus 1 or m is minus h. And m is plus minus 1 means the magnetization direction is 0 or 180 degrees. Okay. And we check it. The second derivative of this energy equation has this form for the theta is 0. And when m is minus h, the solution is always negative. So it's unstable. So this is not the solution. And this is the solution with this condition. So actually, this is the same result which one we already did with these equations. Yeah, this one. I repeated this one for the general case. And this equation tells us when external field H is normal, now we are normalized by the HK. So here one implies the external field is same to the HK. And when theta is zero, means the magnification, we apply the external field to the along to the EJ axis. Then this is the solution with this condition means we are starting here, H is positive, and we have a switching here. And finally, we have this shape of loops. Okay. And once we consider more general case of the theta, unfortunately, there's no honest solution. Sorry, we have when theta is pi over 2, means we apply field perpendicular to the EG axis. Then equation is getting simpler. We have this solution, and we repeat the second derivative condition. We found this solution satisfied this condition, and also M is H solution. Also, there's some chance they satisfy the partial condition. So it means the 90-degree case we have this curve. So this line and in a large field they are saturated. So one funny thing is for the 0-degree we have such a square shape of loops. And for the hard axis applied magnetic field, we have a saturation and the linear one and saturation. But these saturation fields are same. They are identical. And how about the more general angle, not the 0 or pi over 2? In more general case, for example, 10-degree, then they make such kind of loops. And 45-degree, they have this form of loops. And 80-degree, they have loops like this. So if you take a look at this cartoon carefully, you can understand what I'm saying. And in more general case, this one, this equation shows such kind of curve. They have a switching here and saturate and back, and then switching here. So we have a general shape of the loops. Okay, so this Stone-Alpers model can describe basic behavior of the magnetization. Okay. So this animation is my calculation result. You don't need to pay about the red one, just pay focus on the blue one. So we are starting from angle is from 0 to 90-degree. So it's repeated. So this one, the metric code of this calculation is not that long, just maybe less than 100 lines. If you remove the routine for the figure, only 50 lines something is needed to obtain this kind of behavior. So let me show the result. This is the real calculation. You can see the blue one, the switch field is getting smaller and smaller. And finally, they make kind of line. the linear line. Okay. Okay, this is the result. Okay. And then now we are playing with the direction augmentation only easy axis or hard axis or some arbitrary angles. So when the second derivative is positive, this is stable, and when they are negative, they are unstable. So when they change from here to here, the second derivative is passing through the 0 point, right? So that is the switching condition. So this is the second derivative of this general case. And from here, we also need the energy minimization condition. So we have two equations, and we have two with this combine these two equations, we can obtain this result. Here, the theta is the direction of monetization, and Hs is here the given constant. Okay. So in this case, in a polar coordinate system, this is constant, then this curve shows such kind of curves. For example, when theta is zero case, and this is 0, this is 1. So Hs is just 1. So here, and when 90 degrees, theta is 90 degrees, we have this is 1, this is 0, so we have this point, and so on. So we plot it, we make such kind of shape curve. This is called asteroid. And what is the importance of this curve? This means if we apply field to this is the angle, so this is the let's say H parallel, this is H perpendicular to the easy axis. Then the switching field or the saturation field is following this curve, means once you apply the parallel direction with the no perpendicular direction, we have a plus minus 1 over Hs. This is corresponding to Hk. And if you applied only the perpendicular direction with the 0 in plane z-axis, we have a same magnitude of the field need. And what happens if we applied 45 degree? Means the magnitude of the perpendicular direction and the parallel direction are same. Then now we have this result. So now we need only this amount of parallel and the perpendicular direction field to switch it. So means it's more easy to switch it in this direction. So if you have your sample here, applying field this direction or this direction requires switching field of 1. But if you apply field in this direction, your switching field is much reduced. So you can easily see this graph. In 45 degree, you need only this field to switch it. Okay. And this called very important for the field switching devices. And this is the purely mathematical description called the asteroid curve. And this curve is valid for only single domain model, not and also the coherent model. And this single switching model, the Storm-Pass model, the switching field as a function of theta has this form. So we have a minimum at the 45 degree. But in reality, in reality, there is some more incoherent rotation is involved. There's some kind of other structure, but we don't need pay attention for this one. Just pay attention this tonal path model. Okay. And this is also very important in application of MNAM. I very briefly mentioned this monitor resistive RAM, random access memory. And here, if you want switching, for example, this cell, we send current this direction and this direction together. And this cell has a field of the vector sum of these two fields. So they pointing 45 degrees. So they can switching here. But the other one, they have only one directional field. So this is belong to here. So it's far below the switching field. So only this selected cell would be switched, ideal. But the reality is it's not that easy. So when people studying about this kind of MNAM, making such kind of astral curve is very important. But this is not, in reality, this line is very broad. And some cells cannot switch with this given field, or some cell is switching more easily. So if that kind of error occurs, we cannot use it as a memory because we want to write down the specific cells, and we do not want to disturb any the other cells. So that is called the selectivity problem. So we need to select flex cell to write down the information. Okay, any kind of memory application, such selectivity is very, very important. You cannot select a specific cell, you cannot use it as a memory. Okay. So this kind of problem solved by a new technique called the spin transfer torque. But still, the idea of this switching with the Mach field is very important in many applications. So understanding tonal path model is very useful for real research. If you're including more energy term in a tonal path model, for example, exchange coupling or exchange energy or higher order unanswered energy, somehow the basic physics is same. Only difference is numerical details. Okay, so here is energy flux as a function of this energy flux as a function of angle phi. Here, when we think about theta is 0, means the field is applied, the field is the EJ direction. So when no external field, then we have a such energy profile. This is corresponding the cosine, the sine square. Okay. And if you increase field, the curve looks like this, and so on, something like this. And finally, when field is reaching to -1, we have this shape, this curve. Okay. And as you see here, if you are here, this is still stable, but if you little bit increasement of the field, they become unstable point. So they falling down to the lowest energy of the system. Okay, that is the switching. And if you think one more case, the theta is 30 degree, and this curve is corresponding H is 0 case with the angle theta is 30 degree, means it's a kind of shift of the 30 degree of angle of the sine curve, sine square curve. But once you apply the field, this minimum portion is little bit shifted. Okay. So at the middle point, the direction of the spin, the magnetisation is not 30 degree anymore, because the unanswered energy free for the angle, this angle, but sorry, the field is free for this angle, but the the analytic energy flip toward the other direction. So when we have this point, they are become unstable. So they are switching here. So we obtain the smaller switching field. Okay. Okay, so far we learn about the Stone-Warp's model, which one is we assume the single spins or monospin or macro spins. So there is no domain work because we have only one domain. But in reality, domain work motion is very important. So in real sample, the switching field is strongly dependent on the domain work motion. So we're gonna learn about this. And also the pinning or defect or non-uniformity of your sample play very important role determining the switching behavior. And also incoherent rotation is involved. And with the Stone-Warp's model, this idea, we can find of the switching of the spin transfer torque also. Yeah, this is the I will gonna give a lecture about when we learn about the spin transfer torque. But anyway, even though the Stone-Warp's model is too simple, but still there are many lessons we can obtain from this model. So I strongly ask you to try to understand this Stone-Warp's model. Okay? And in a reality, there is a very famous paradox called the Brown's paradox. Because according to this Stone-Warp's model, switching field must be same as the analytic field, this value. But in reality, the experimental measurement of coercivity is much smaller than this analytic field. This means it's a failure of this macroscopic model. And there are many reasons why this Brown paradox appeared. But there are so many reasons, so it's not easy to simply say. But still, this number is very important. And also experimental measure the HCC is also important. And you're gonna learn why this process can be happens by introducing the micromagnetic models. This reality. So micromagnetics is kind of the motion of the spins with small cell magnetization. Now, in Stone-Warp's model, we assume this like the motion of the magnetization is a single spin. But the reality is they are consisted of the many spins. So we need to solve this kind of behavior by help of the modern computer. This is what is called the micromagnetics, which one is also very important tool in modern spin theories. Okay, yeah, a long time ago, this micromagnetics is really heavy computing. So only few theorists involved this kind of a study. But nowadays, the help of the powerful modern computer, any student can do it. If you choose the proper tools and proper simulator, and also, fortunately, there are many open source simulator, so you can download it and you can do it by yourself. Okay, so there is a big difference between the micromagnetics and the Stone-Warp's model, but maybe this is not the good time to explain it. I'm going to explain it later when you learn about the Landau-Ricci-Gilbert equation, which is also another master equation of the spin dynamics. Okay, today I'm going to stop here because yeah, this is just the eve of the Chuseok. Yeah. Okay. So, do you have any questions? No. Okay. So, please enjoy your holiday and have a good food. Do not get too much weight. 자, 추석 잘 보내고요. 다음 주 수요일이죠? 다음 주 들어봅시다.